we've learned to solve a few different types of equations. And if you want the appropriate section numbers to look up how to solve linear or quadratic or polynomial or rational equations, there they are. But today, we're going to learn to solve what we call radical equations, power equations, absolute value equations, and equations that are quadratic in form, which is always the trickiest topic in this class. And then later, we'll still have some more equations coming up this semester. But altogether, this is your grand list of all 10 types of equations you have to be able to solve by the end of the semester. It's not that bad. Especially, I think, today is fine. This is called a radical equation. It's a radical equation because it's an equation and it has the little radical symbol. So radical is talking about that thing. To solve a radical equation, you got to remember to do two things. And step number one, we want to isolate the radical. What I mean by isolate is I want just the radical on one side of the equation, and everything else is going to be moved to the other side of the equation. That way the radical is all by itself. And to do that, I might subtract 2 from both sides. And when I subtract 2 from both sides, I get that. And who can guess, what am I going to do in step 2 here?
Square both sides.
Yeah, square both sides. So I'll square the left side, I'll square the right side. And on the left side, I just get the radicand, which is 2x minus 1. And on the right side, you have to think about foiling this, or maybe you draw a box like we've done earlier in the semester. And x minus 2 times x minus 2 will give you x squared minus 4x plus 4. Those are the two steps that you really have to remember. First, isolate the radical, then square both sides. And now there's no more radical, right? So what type of equation is this now? Yeah. If I go back to my little list of equations, I think, well, now what am I dealing with if it's not a radical equation? Now we've simplified this down to a quadratic equation. And you can solve this quadratic equation just like we did back in section 2.4. You've got options. You say, okay, I need to move everything to one side of the equation. I'll make the other side of the equation just equal to 0. And that means I subtract 2x from both sides. I add 1 to both sides like this. And at this point, it's up to you. You can either use the quadratic formula to give you your answer, or you could just factor it. If you think factoring is faster and easier, then you can factor. If you think using the quadratic formula is faster and easier, then you can use the quadratic formula. This one factors as
3, 2.
well, negative 3 times 2 gives me a negative 6, but I needed the product to be a 5.
Negative 2.
We need it to add up to negative 6,
Negative 5 is negative 1.
but multiply to give me 5. So yeah, this one would be negative 5 and negative 1. Again, negative 1 times negative 5 gives me the positive 5 that I need, but negative 1 plus negative 5 gives me the negative 6. Has to add to equal your b and multiply to equal a times c. All right, so then now that this is factored, I can see that my two solutions here are positive 1 and positive 5. Now here's the weird part. Whenever we have a radical equation, you absolutely must check your answers. Because sometimes you get good solutions, and sometimes you get bad solutions. And you would like to know if you found a bad solution. Now, checking your answers is pretty easy. Same thing as we've always done. You take the solution, x equals 1, and you plug it into the original equation. What happens if I plug in x equals 1? This would be the square root of 2 times 1 minus 1, right? Plus 2 equals 1. I just plugged in the solution x equals 1 to see if it was going to work. But is that going to work? No. Because the left side of my equation is equal to 3, the right side of my equation is equal to 1, and that means x equals 1 is a bad solution. There was nothing wrong with the way we found that solution. We didn't make any mistakes. But with radical equations, you can still sometimes find these solutions without making any mistakes at all that don't work with the original equation, right? This is the equation we're trying to solve, and that one clearly just doesn't work. What about my other solution? My other solution was x equals 5. Well, that would give me 2 times 5 minus 1 plus 2, or sorry, square root plus 2 equals 5. Does that one work? Because on the left side, I've got the square root of 9, which is 3. 3 plus 2 is 5. So that actually works. So this is a good solution. It actually works with my equation. Radical equations are really maybe the only place where this shows up. I'm trying to think really quick. But you don't get this phenomenon with linear equations, quadratic, polynomial, rational. I mean, you could make up rational equations that have weird situations, but we won't see those in this class. But radical equations, you definitely have to check. As far as I know, you don't really have to worry about this with most power equations, not the ones we're going to see in class. Absolute value is fine. Quadratic and form, that's fine. Exponential and log, that's fine. This is really the ones where you have to worry about having these bad solutions. Some math textbooks would call these extraneous solutions. And so maybe in a previous high school class you've heard of extraneous. That's just a really long word that means bad. Yeah, it's like asymptote. Nobody knows how to spell it. So it just means bad. Let's try another one. Also a radical equation because I've got the radical. What's my first step here? Isolate the radical. We want the radical to be by itself. And so we make it all by itself. If I do that, what does the right side of my equation look like? Perfect. X minus 3 over 2. And that was my first step, isolate the radical. What's my second step? Square both sides. So let's square both sides. And then the left side of my equation becomes And the right side of my equation becomes that's 9 over 4. Very good. And now I have a quadratic equation. The first step in solving a quadratic equation is to
One side.
move everything to one side. So let's move everything to the right side. The right side is going to be x squared.
Like 77 over 4.
77 over 4. Yep. So 17 times 4 is 68. 68 plus 9 is 77. So after you find a common denominator and you add 17 plus 9/4 is 77 over 4. Okay, now at this point we can either use the quadratic formula or you can factor this. Quadratic formula might be the simpler way to think about this, right? And so, you know, we've got something that looks like this, and that means my solutions are going to be negative b over 2a plus or minus the square root of b squared minus 4ac divided by 2a. So negative b means negative negative 9, which is positive 9. A is just 1, so that's 9 halves. B squared would be negative 9 squared, which is 81, minus 4 times 1 times 77 over 4 is 77. (81) minus 77 is 4. Square root of 4 is 2. 2 divided by 2 is 1. So I've got two solutions, which are 9 over 2. Oh, sorry, not 9 over 2. 7 over 2. And 11 over 2. How did I get one? Okay. Okay, so you guys have solved these quadratic equations before. The real skill is remembering if you see a radical equation. Radical means you isolate the radical and then you square both sides to get rid of it. What else? We still have to check our answers, right? We still want to plug in 7 over 2 and see if that works. And this may be something that you want to do in your calculator. If you bring a TI-30X2S and plug this in, 6 times 7 over 2 would be 21. So we're talking about the square root of 21 minus 17, which is the square root of 4, which is 2. 4 times 7 over 2 is 14. So I've got 2 minus 14 plus 4, which is, I think, negative 8 on the left side. And on the right side, we've got negative 3 times 7 over 2, which is negative 21 over 2, plus 5 over 2. Negative 21 plus 5 is negative 16 over 2, which is negative 8. And so this is actually a good solution. When I plugged in x equals 7 over 2, I found that the left side of my original equation equals the right side of my original equation. What about my other solution if I say x equals 11 over 2? So I plug it in the same way. I say, well, on the left side I've got 6 times 11 over 2, which is 33, minus 17. And 16, and the square root of 16 is 4. Oops, that's not equals. That's minus 4 times 11 over 2, so that's minus 22, plus 4. So altogether on the left side, I've got, it's like 4 plus 4 minus 22. I think that's minus 16. On the right side of my equation, I've got negative 3 times 11 over 2, so negative 33 over 2, plus 5 over 2. Which would be negative 28 over 2, which is negative 14. This seems pretty close, and I think I even made a mistake. I think the left side of the equation is negative 14. So I think this is also a good solution. You just got to take your answers and you got to plug it back into your original equation. Sometimes, like in the previous example, you get one good, one bad, and sometimes you plug it in and you get that both of those solutions are good solutions. Maybe there's even a possibility that you get 2 bad solutions. Maybe I'm wrong. I don't know if that's actually possible, but. By the way, if you're wondering how do I check my work, or what's a good way to check my work, maybe I could plug in both sides of this equation into Desmos and see what that looks like. And this is our first example. I've got square root of 2x minus 1 plus 2 equals x. Oh, so the right side of the equation is x. So again, back to the first example, the left side of the equation is plotted here in red, the right side of the equation is plotted in blue, and where the right side is equal to the left side, that's the point where these curves intersect each other. So if you look at the intersection, it should give you the x value of the solution, right? The x coordinate should be the solution. And the x coordinate is 5, and we found that 5 was the only good solution, right? What about the bad solution? How do we end up with a bad solution? You can get the bad solution if you complete the parabola. Right? Whenever we do the square root, which is in red, we only think about taking the positive square root. But if you actually take the negative square root, it finishes out the parabola shape. It's just on its side. And that bad solution, that's not actually a solution to your equation, was x equals 1 for the first example anyways, right? And that's exactly what we got. So we got x equals 5 was good, x equals 1 was bad. In my second equation, I got square root of 6x minus 17 minus 4x plus 4. That was the left side. The right side is negative 3x plus 5 over 2. And so this, the left side of the equation is given by the red curve, which is not super easy to see. I know there's a way I can make this easier to see. Or so I thought. It was very close. Okay, well anyways, these curves intersect at an x value of 3.5, or 7 over 2. Perfect. And they also intersect at 11 over 2. And so both of these are good solutions because I didn't even have to invoke the negative square root part, right? If I actually copied this down and then put a negative sign in front of the square root, that would give me the bad half of the curve, but actually, in fact, the line intersects both of the good parts. So parabolas don't have to be vertical. Sometimes they can just be sideways or diagonal or not. Okay, moving on. So you've seen two examples of radical equations. Now we're moving on to what I would call a power equation. And I'm calling this a power equation because this equation contains x raised to some non-integer power, right? If it were an integer power, this would be like well, it could be a polynomial if it's a positive integer, or it would be a rational number if it happened to be a negative integer. But if you've got like a weird power like 3/4, this is not a polynomial, it's not a rational function, this is something else. Now, how do I find the solutions? I'm going to isolate x raised to whatever weird power you have. And that means I could start by adding 24 to both sides, and then proceed by dividing both sides by 3. And now, it's really important that you remember something we did early on in the semester. It was the third day of class. If you want to look in your section 1.3 notes, this is where it would be. The important thing to remember is that if you have a fraction in your exponent, well, the numerator of that fraction behaves like any other exponent, but the denominator of that fraction tells you what root to take. So if I've got a 3/4 exponent, the 3 is just a power, but the 4 tells you to take the 4th root of x and then raise it to the 3rd power. So that means for my equation, what I'm really looking at on the left side is the 4th root of x raised to the 3rd power. And as I continue to solve here, I think, how do I get rid of that 3? I could take the cube root of both sides. So here is me taking the cube root of both sides. And on the left side, I'm left with the 4th root of x, because the cube and the cube root cancel each other. What's the cube root of 8? 2. Because 2 times 2 times 2 is 8. Now I ask, how do I get rid of that 4th root of x? How do I just get down to the x part? Yeah, I can raise both sides of my equation to the 4th power. So on the left side, the cube root raised to the 4th power, that cancels out, and I just get x. On the right side, what is 2 raised to the 4th power? 16, because it's 2 times 2 times 2 times 2. That is 16. Questions? No? Okay. So we got one more of those as an example. Same idea. I want to begin by isolating x to the weird power. And in this case, I would add 3/4 to both sides. And negative half plus 3/4 is positive 1/4. And then I think, well, x raised to the 2/3 power, that is the cube root of x raised to the power 2. And now what do I do? Square root of both sides. So, don't forget the square root principle. The square root principle says if you're about to take that square root, make sure you throw in a plus or minus sign. On the left side, I just get the cube root of x. And on the right side, I get plus or minus what? 1/2. Now, to get my answer, I need to cube both sides. So raise both sides to the power 3. And on the left side, I just get x. On the right side, I get positive half raised to the 3 power is positive 1/8. And then negative half raised to the 3rd power is negative 1/8. So there's actually two solutions, right? I could say x equals positive 1/8 or x equals negative 1/8. Questions? Still good? All right, so we're halfway done. The next equation type is super duper easy if you can remember what we're doing. These are absolute value equations. So this one says, if I have 2x minus 3 and I take the absolute value of that, I want it to be equal to 11. We can remove the absolute value on the left side if, on the right side, I acknowledge that this, all the stuff inside the absolute value, could be positive or negative 11. Right? Because if 2x minus 3 is positive 11, then taking the absolute value remains positive 11. It's like the original equation. And if 2x minus 3 is negative 11, then when I go to take the absolute value, it becomes positive 11, and that still satisfies my original equation. So if you want to get rid of absolute values, just make sure you throw in the plus or minus on the opposite side. And then we solve for x like normal, so I might add 3 to both sides. Keep in mind that you don't make that plus or minus 14. Because the 3 is not part of the plus or minus business, right? The 3 is going to be strictly positive when I add 3 to both sides. And then I divide both sides by 2. And I get 2 answers, right? One of them is 3 plus 11 over 2. And one of them is 3 minus 11 over 2. So those are the 2 answers. I know that I put indicate whether each solution is good or bad, but you don't have to worry about that for absolute value equations. I think they're always good. Never hurts to double check though, right? Checking your answers, that couldn't ever hurt. If you've got time to check your answers, I really highly recommend taking the time to check your answers on a test, just to make sure you got it right.
How'd you get 7 and
3 plus 11 is 14, and 14 over 2 is 7. 3 minus 11 is negative 8, and negative 8 over 2 is negative 4. You feel good? Makes sense? Okay. I'll show you one more and then we'll move on. Same kind of deal. I want to start off by isolating the absolute value. I didn't have to do that in the previous example, but in this case, I do. In the previous example, it started off already isolated. But this time, I would have to start by adding 15 to both sides. And then I would divide both sides by 5. That's essential. Because now that we've got the absolute value isolated, how do I proceed? How do I get rid of the absolute value? Yep. I write on the left side plus or minus 3. And on the right side, that allows me to get rid of the absolute value. What do I do next? I'll have to subtract 1 from both sides. And please keep in mind, this does not mean I do 3 minus 1 and write plus or minus 2. That's not the same thing. When I say I'm subtracting 1 from both sides, that means I really do have a solid negative 1 on the left side, and it's not part of the plus or minus 3. That's the only possible way you could get tripped up, I think, on these kinds of questions. And what do I do last? I have to divide by negative 4. So negative 1 divided by negative 4 is positive 1/4. And 3 divided by negative 4 is negative 3/4. But of course, I'm considering both the positive and the negative anyways. So you don't have to worry about keeping a negative sign around, right? And that's my answer. So I've got 2 answers. One of them is x equals 1. Yeah. The other one is x equals negative 1. Okay, any questions? Okay, so we did radical equations, we did power equations, we did absolute value equations. This is the trickiest one of all. Save the best for last. These have the name quadratic in form. The reason that these are called quadratic in form is because someone decided this looks almost quadratic, and I could make this into a quadratic equation if I do a little substitution. So I'll show you what that means. I look at this equation, and the first thing I think to myself is that back in section 1.3, we decided x raised to the 2/3 power was just like the cube root of x raised to the 2 power. Because the 2 in the numerator goes like normal, but the 3 in the denominator becomes a cube root whenever I have a fraction exponent. Then I have plus 11 times the cube root of x. Then I have plus 2 equals 0. And again, I'm thinking to myself, I could actually make this equation into a quadratic equation if I allow myself a little substitution. And the substitution I want to make says y equals the cube root of x. So I made this up. This is not something that anyone is going to tell you. It's not going to say it on the test. But you have to decide yourself that you're going to do this kind of substitution. And you do this because you want your equation to look like this. Instead of cube root of x squared, Now it's just y squared. 11 times cube root of x becomes 11y. And the great part is that this is a quadratic equation. You choose your substitution in such a way to make a quadratic equation. We like quadratic equations because we learned how to solve them earlier in the semester. And so maybe you factor this, or maybe you do the quadratic formula. I'm thinking maybe I'll just do the quadratic formula, because at least I know the quadratic formula always works. And that gives me negative 11 over 10 plus or minus the square root of b squared, that's 11 squared, minus 4 times 5 times 2 over 10. And so I've got two solutions to this quadratic equation in terms of y. One is negative 11 over 10 plus or minus 3 over 10, right? I'm thinking to myself, 121 minus 40 is 81. The square root of 81 is 9. Oh, I took too many square roots. So it's negative 11 over 10 plus 9 over 10. That's negative 2 over 10. Of course, 2 over 10 simplifies to 1 over 5. And then the other one is negative 11 over 10 minus 9 over 10, which is negative 20 over 10. And that simplifies to negative 2. Okay, so I've got these two solutions. I can write y equals negative 1/5, and also another solution is y equals negative 2. Let's zoom out and look at the grand scheme of things. I'm not done yet. And I'm not done yet because my original equation wanted me to find a solution in terms of x. What x value satisfies that equation? I only found a y value that satisfies a different equation. The connection here between these answers and the answers I really want is that I defined y equals the cube root of x. So I'm not done yet. To connect this back to the real solutions that I actually want, I have to replace the y's with the cube root of x. And I'll write cube root of x equals negative 1/5, and the cube root of x is equal to negative 2. I can solve that equation for x. I just have to raise both sides to the power of 3. What's negative 1/5 raised to the third power? Very good. And then this one, if I raise negative 2 to the power 3, negative 8. And finally, these are the actual solutions in terms of my x variable that satisfy my original equation. Once you know what substitution to make, these aren't hard. I don't think anyways. I mean, you know how to solve a quadratic equation. And at the very end, reversing the substitution, that's not too bad. What I see students struggle with most often is they look at this and they think, I don't know what to do, right? Maybe they don't know what substitution to choose, or maybe they don't even know that they're supposed to be choosing a substitution, right? And the only thing I can say is it takes practice, right? That's why we have homework pages. It's not for my benefit. It's just to provide you something to practice with. And the other thing I will tell you is that there's a limited number of equations I'm going to ask you about on a test. In fact, for the rest of the semester, there's only 10 types of equations I could ask you about. So if you know how to identify linear, quadratic, polynomial, and rational equations, you know how to identify radical power and absolute value equations. If you've got an equation that doesn't look like any of those other things, chances are you need to find a substitution to make it a quadratic, you know? That's the only thing I can tell you is if you don't know of another strategy to solve the equation, then maybe start thinking about how could I substitute to make this a quadratic equation.
On like something else.
Mm-hmm. Yeah, I've got more examples for you. Like this one. You know this is going to be a substitution, even though this is technically a polynomial, right? So with a polynomial equation, you could use like the rational root theorem to make a list of possibilities, and we can go down that route, synthetic substitution, blah, blah, blah. But this one is special. You could solve it with the rational root theorem, but there's another way I can solve this. Because x to the 4th power is just x squared squared. And that means one substitution I could actually use here is to say y equals x squared. And then I could rewrite this as saying y squared minus 8y minus 9 is equal to 0. This one factors really nicely. As y minus 9 and y plus 1. And that means I have a solution that's y equals 9 and another solution of y equals negative 1. Of course, I don't care what y is. What I really care about is what is x, you know? I need to find my solution in terms of my x variable. And so to find that solution, I just have to use that substitution, and this time I'll replace every y with x squared. So I write x squared is equal to 9, and x squared is equal to negative 1. I'm going to have 4 solutions in total. X squared equals 9, that has 3 as one of the solutions, right? 3 squared is equal to 9. What's another solution? Negative 3. And there's 2 more solutions. What squared is equal to negative 1? I and negative I. Because the square root of negative 1, that's the definition of I, and the square root principle also gives us the negative I equation. So 4 solutions altogether. And I'll repeat myself and say that, you know, this is a polynomial equation, right? The x to the 4th makes it a polynomial. Only integer powers of x here, or natural number powers of x. So you could have used the rational root theorem. If you used the rational root theorem, maybe you would try out 3 and you found that 3 was a root. And you could factor that out, and then you would end up with a cubic polynomial, and you use the rational root theorem again, and you would have found that maybe negative 3 was a root. You could factor that out and end up with a quadratic polynomial, and then you could use the quadratic formula to find the last 2 roots. So rational root theorem would work for this, but also, you know, sometimes a little trick like a substitution can get you the answer faster. It doesn't always work for polynomials, but it does work for some polynomials. Any questions about that one? No? All right. One more, and then you're free to eat lunch. This one's a little bit more suggestive about what to do. Once again, this is a polynomial. if you wanted to go through the effort of expanding this out on the left side of the equation, you would end up with not a quadratic, you'd end up with a quartic polynomial, degree 4 polynomial. And you could solve it with the rational root theorem, blah, blah, blah. But I think the way that this is written, it's almost obvious what to do here. What kind of substitution is this suggesting? Yeah, y equals x squared minus 5. And then I get y squared plus 3y minus 10 equals 0. And that's so nice and neat. This factors really easily. It factors as y minus 2 and y plus 5. And after factoring this, I know y equals 2 or y equals negative 5. But remember my substitution, I said y is equal to x squared minus 5. So what I should really write over here is x squared minus 5 is equal to 2. And over here, x squared minus 5 is equal to negative 5. Over here, x squared equals 7. Over here, x squared is equal to 0. So my solutions this time are square root of 7, negative square root of 7, and 0.